Hello and welcome. Differentiation under the integral sign, and we're going to be dealing with this particular integral today by using these special techniques which normally are being taught at undergraduate level. Sometimes there are still universities that do not really bother with this, so it's probably even at university level a little bit of enrichment if you want. Okay, first of all, this particular integral, we will assume that it actually converges because it's actually improper. If you look at what happens in there, when we're putting, of course, the zero in the log, we have a problem. And also when we're putting 1 onto the log, again we have a problem because of course the log of 1 is 0 and the log of 0 is negative infinity. So we'll assume convergence and we're going to see how we're going to deal with this particular integral. Okay, we're going to define the integral I as the integral from 0 to 1 x to the 1 over the log of x, but we're going to introduce a parameter. A parameter is, we're going to go on to the x here. You can call k, t, whatever. Let's use k there, dx. And of course, this particular integral now is a function of k. Don't forget, this particular integral is a function of nothing. It's actually physically just a number if you want. But the moment we put a k, this will produce something which is going to be something k. And of course, our integral will be, when we put k is equal to 1, it will become the integral we're trying to find. But for the time being, we need this parameter. What we're going to do is, and why do we put this parameter? Because if we differentiate x to the k, that's the rationale, if you want, behind all of this. But with respect to k, this will produce x to the k times the log of x. And this log of x, of course, would clear this item, that unwanted item, this awkward item, if you want, that we have on the denominator. So our next line, of course, I just wrote it up there, is to differentiate both sides with respect to k. So d by dk of I as a function of k is of course d by dk 0 to 1 x to the k minus 1 log of x. Now we can interchange the differentiation and the integration there by Leibniz integral rule because we have constant limits. However, once that d by dk goes in there, technically it should become a partial because of course once it goes inside, this will be a function of two variables. So it's a little technicality. You can leave it. Sometimes I actually write partial even here and partial there. It doesn't really matter. I'm a little bit sloppy with my notation at times. So d by dk, and we have now x to the k minus 1 over the log of x dx. And if we differentiate that with respect to k, this of course is a constant, so we can actually write it outside the partial if you want, 1 over the log of x. And this will differentiate, as we said a few minutes ago, to x to the k log of x, and of course the minus 1 will disappear and we have dx, and of course the log of x is cancelled. So let's see what we got so far. We have d by dk of I to the k in the simplest form that we got from here is in fact equal to the integral from 0 to 1 of x to the k, which of course, with respect to x, which of course is a very, very easy integral. What does that integrate now to is, I'm going to do in this line, we're going to increase the power by 1 and divide by the new power. Should be k there. I was about to write x. Do apologize. K plus 1 between the limits of 0 and 1. And of course, we're putting x is equal to 1 in there. It's going to give us 1 over k plus 1. And if we put x is equal to 0, this will vanish. So all of this is 1 over k plus 1. But we haven't found that integral, I of k if you want. This so far, let me just make some room. actually I might be able to squeeze it one more line further down. What we found is that d by dk of I of k turned out to be 1 over k plus 1. The easiest of integrations, so we can integrate both sides with respect to k. So I of k is going to be equal, of course, to the log of k plus 1 plus some constant. So let's return, because I of k, of course, is that line up to the very top, and let's say, okay, our I of k is in fact equal to the log of k plus 1 plus c. And of course we have this new thing now, this constant c, which we need somehow to work out. So how are we going to work this out? The time it takes me to rub off the board, see if you can think of some suitable value we can put for the k in this expression here, which will allow us to evaluate the constant. So for example, if k is equal to what? Can we put k is equal to 0? Well, we can. Let's have a look what happens. If k is equal to 0, we're going to have, of course, I of 0 is equal to the integral from 0 to 1 x to the power of 0, which is of course 1 minus 1 divided by the log of x dx, which of course is going to be the integral of 0. It doesn't matter, the answer will of course be 0. So when we're putting k is equal to 0, our integral, the whole thing becomes 0. So what does that say? It says, let me just make some more room again. 0 is equal to, so this has become 0 when we're putting k is equal to 0, but we can have to put 0 there as well, the log of 1 plus c. But of course the log of 1 is of course 0, so the constant in this particular case will be 0. So finally we have actually come to the conclusion that the I of k is in fact the log of k plus 1. So in our case, remember I of k is defined as this integral here, and what we were after this particular expression. We're getting our integral, of course, if k is equal to 1. So I of 1, if you want, which stands for the integral 0 to 1 with k is equal to 1, x minus 1 over the log of x dx is going to be equal, of course, to the log, we're putting 1 in there, the log of 2, and that is our answer. Okay, I just want to say something about this particular integral. If you go to my site and look at the booklets, advanced, and I think it's the actual file is called differentiation under the integral sign, you will find, I think, this particular integral. You will find it, I think, also to the power of 4. You will even find it as x to the a, perhaps. The answer of the work is in fact are identical. Here, in fact, putting an a there for where a can be some kind of constant if you want, we can use it actually as a parameter, and the answer we're going to get for all of this is of course k plus 1, or if you're using a plus 1, so in general form if you want. So they all form and follow exactly the same procedure. I've done it with x is equal to 1. What if it was a 4 in there? I think that's a different question, on, as I just mentioned in my book. Well, the answer, of course, when we would have reached that stage, it would have been the log of 4 plus 1, so that would have been the log of 5 for that particular integral, and so on. Then the method is identical. I hope you find it interesting. I hope you find it useful. And who's laughing now? I certainly am.